In this video, we're going to discuss how the T and F tests generalize when we move from a bivariate regression model to a multiple regression model. Once again, we're assuming that anyone watching this video is familiar with how to conduct T and F tests in the bivariate regression model. If you're not comfortable with that, go back and review those earlier videos before watching this video. In general, everything that we talked about in terms of t-tests in the bivariate case generalizes very directly to the multiple regression case. The only difference in practice is that when we're performing tests on individual intercept or slope parameters, is that instead of the degrees of freedom being n-2, it takes this more general form of n minus a quantity, k plus 1, where k is the number of independent variables, and we add in 1 for the constant term. So the quantity k plus 1 is a total number of estimated parameters, and n minus k plus 1 is the degrees of freedom for each of the individual parameter estimators. So all that discussion involving one-tailed tests and two-tailed tests and so forth all transfers very directly, with the only difference being the number of degrees of freedom used for hypothesis tests. And we should also note that the case that was discussed in the bivariate model fits this more general model. So that's a special case of the more general formula that's used here. We also discussed the use of an F-test for goodness of fit. The same type of test can be used in a multiple regression model, except now instead of testing for whether the single independent variable has a significant effect on the dependent variable, we're testing whether the whole set of independent variables have some effect on the dependent variable. The null hypothesis states that each and every one of the independent variables has no effect on the level of the dependent variable. That null hypothesis can be rejected if at least one of the independent variables has an effect which is not equal to 0. So this is a pretty minimal test. What it's testing for is whether at least one variable has some impact on the variable you're trying to explain. If you can't reject that null hypothesis, your model is probably not a very useful model. The formula that we use is this. It looks very similar to what we used before, except now we have k in there, where in the bivariate case, we had just used 1. In the numerator, we take the regression sum of squares, that sum of squares that's explained by the regression, and we divide that by its degrees of freedom, which is the number of variables we use to compute that. In the denominator, we take the error sum of squares, the sum of squared error terms in the regression, and we divide that by the degrees of freedom for the error sum of squares, which again is n minus a quantity, k plus 1. We reject the null hypothesis that there's no effect if the estimated F statistic exceeds the critical value for an F statistic at the selected significance level. The numerator degrees of freedom for the F statistic is the number of slope parameters, k, and the denominator degrees of freedom, again, is n minus a quantity, k plus 1, or n minus the total number of estimated regression parameters. As before, we can note that there's a relationship that exists between the value of r squared and this F statistic, and given the definition of r squared, it can be shown with a little bit of algebra that the F statistic can be computed as r squared divided by 1 minus r squared times a quantity, n minus a quantity, k plus 1, divided by k. The F test becomes a lot more powerful in the multiple regression model. In particular, we can use it to test linear restrictions on one or more parameters, so we can test the relationships that exist among the parameters of a model. The type of test that we'll be using initially is called a Wald test. Let's examine some examples of tests of linear restrictions on parameters. One way we could use this is to test to see whether the magnitude of the effect of one independent variable on the dependent variable is the same as the effect of another variable. If we're trying to determine whether the effect of the variables x1 and x2 are equal in magnitude, we do that by just testing the null hypothesis that beta 1 equals beta 2. If we cannot reject that hypothesis, that suggests that the effect of those two variables are not significantly different from each other. If we can reject that, though, that would tell us that there is a statistically significant difference in the magnitude of the effect of x1 and x2. Another type of test we might perform is something of the form that beta 1 plus beta 2 equals 1. So if there's a hypothesis that suggests that the sum of these coefficients add up to some specific value, then we can simply impose that restriction and test it. One case where we'll be seeing that a bit later in the course is to test for constant returns to scale in a production function, and we'll come back to that in a later chapter. Or more generally, we could test for any linear restriction on parameters, such as beta 1 plus 4 times beta 5 equals 0, or anything that has some meaning in the model that you're trying to analyze. One of the most common uses of the Wald test is to test whether a set of coefficients is 0. In this case, we're testing whether the variables x4, x5, and x6 jointly have any effect on the dependent variable. And if we can't reject this null hypothesis, that suggests that as a group, those variables are not important in this particular equation. And this is commonly used when you're testing alternative model specifications, which is a topic we'll return to in a later video. The way we conduct a Wald test is we first estimate a restricted version of the model that takes into account the restriction in the null hypothesis, and we save the error sum of squares from that restricted version of the model. We estimate also the unrestricted version of the model, and we save the error sum of squares in the unrestricted version of the model. We define M as the number of linear restrictions. That's the number of linear constraints that are imposed on the parameter estimates. In general, this is going to be equal to the number of equality signs in the null hypothesis. Once we've done that, we compute the Wald statistic, which is defined to be the error sum of squares in a restricted model minus the error sum of squares in the unrestricted model divided by m in the numerator, and in the denominator, we take the error sum of squares in the unrestricted model, and we divide that by the degrees of freedom for that, which is again n minus a quantity k plus 1. This is distributed as an F distribution with m degrees of freedom for the numerator and n minus k plus 1 degrees of freedom for the denominator. And looking at this equation, we can note that if the restriction is true, the restricted version of the model should have errors that are comparable in magnitude to the unrestricted version of the model. In that case, the numerator will approach 0, and we'd have a low value of the F statistic. However, if the restriction is not appropriate, the restricted version of the model is going to have substantially larger squared error terms, and as a result, the numerator will tend to be relatively larger. And we reject the null hypothesis if the value of the F statistic exceeds the critical value at the preselected significance level. Let's take an example of ways in which we could impose these restrictions. Suppose we take a simple model where we say that y is a linear function of x and z, and we wish to test a hypothesis that the effects of x and z are identical. So we're testing whether beta 1 equals beta 2. The way in which we create the restricted version of the model is we substitute that restriction into the original equation to form the restricted version of the model. In this case, when we do that, if we replace beta 2 by beta 1, we get y is equal to beta 0 plus beta 1 times the sum of x and z. Or alternatively, we could just as easily have said y is equal to beta 0 plus beta 2 times the sum of x plus z. Now, one thing that will happen is that if we have one restriction, the new equation will have one fewer independent variable on the right-hand side. If we have two restrictions, there'll be two fewer. So whenever we have some restrictions, we're going to end up with a restricted version of the model that has fewer variables on the right-hand side. The way you would estimate this in any econometrics package is you would simply create a new variable that's equal to the sum of x plus z, and you'd run a bivariate regression in this case of y on this newly created variable and the constant term. The number of restrictions in this case is just 1 because we're only imposing that one linear restriction that those two parameters are equal to each other. Another example of the use of linear restrictions, and this is a very common one, is suppose we have a linear relationship between y, x1, x2, and x3, and we want to test the null hypothesis that beta 2 equals beta 3 equals 0. So we're essentially testing two restrictions here, that the variable x2 has no significant effect on the dependent variable, and similarly, that x3 has no significant effect on the dependent variable. What we're testing is whether the joint effect of variables x2 and x3 together is truly 0. In this case, the restricted version of the model is fairly simple. We just substituted in values of beta 2 and beta 3 equal to 0, and the restricted version of the model is that y is equal to beta 0 plus beta 1 times x. And then you just run the two models, compute the error sum of squares in both, take the change in the error sum of squares. The number of restrictions in this case would be 2 because we've imposed two linear restrictions. So we divide the change in the error sum of squares by 2, and then we take the error sum of squares in the unrestricted model and divide that by n minus 4, because in this case there are 3 slope variables plus the constant term in the unrestricted version of the model. This type of test is used very often when we're trying to test to see whether a set of variables is jointly significant. You may have already noticed that the test of goodness of fit that we discussed earlier is just a special case of the Wald test, in particular that last example we talked about, except now we're testing for the joint effect of all of those variables. So if you remember how to do a Wald test, the F statistic, or the F statistic for the regression, is effectively just a Wald test for that whole set of slope parameters.